Alright, so I didn't have time to finish explaining phase change diagrams. See if I can find a good one online. Phase change diagram. So here's one, can y'all see it? So this is so we can plot pressure and temperature, and measure whether or not something is a solid, something is a liquid, something is a gas. So temperature is going in the horizontal direction. So if we pick a random point and go to the left, we'd expect eventually we'll reach the solid phase. So the solid phase is usually going to be at the lower temperatures. Likewise, toward the right, we end up having more gas. Somewhere in the middle, we have a liquid. I don't know why this dashed line here, you can ignore it, it's this one right here. So the liquid phase is between this green line and this blue line. So let's see if I can actually look up the one I had yesterday for water. Alright, so here's one of water. Here's a few more. So again, like if we were down to 10 pascals, water would not exist as a liquid. As we increase temperature, it would immediately go from a solid to a gas directly, so it would ablime. At 1 atmosphere of pressure, we have water freezes at 0 degrees and boils at 100. If we were to increase the pressure, we could push the water vapor down and keep it a liquid for longer. So as we increase the pressure, the temperature at which it starts to boil increases. If we reduce the pressure, that temperature will drop. We have two major points. One is called the triple point. The triple point is the point in which a substance can exist as a solid, a liquid, or a vapor. The other point is something called the critical point. This is the only two things you really need to know. Triple point, it can exist as all three phases. During the critical point, or definition of a liquid and gas disappears. Anything that has a hot, anything in this upper region right here, we call a supercritical fluid. It no longer acts like a liquid and no longer acts like a gas. It acts like both. It acts both like liquids and gases combined. So it tends to spread out, but also at the same time it tends to stay together. It's very weird, but anything after this point we really can't call liquid or a gas. If we lower the pressure and get below this point, it'd be gas, and they also have vapor. We can still call it vapor gas too. So anything below here. So looking more at like this region right here. Again, we have the below. So at the lower pressures, it's gas. At the lower temperatures, it's a solid, and in between is a liquid. If anything past this critical point, it is no longer liquid or gas. It's called a supercritical fluid. So this is a carbon dioxide. Carbon dioxide or dry ice. It's a solid. This all starts at 200. So it's a gas between 200 and 400 degrees Celsius. Its triple point is somewhere around 8 atmospheres of pressure. And its critical point is around, this is in bars actually. So bar is about an atmosphere. So you would have to go almost to 100 atmospheres of pressure at 300 degrees Celsius to get it into a supercritical fluid. That's a lot of pressure, 100 times atmospheric pressure. So let me make something up. Alright. Which phase would this be right here? So again, this is temperature, and this is pressure. So which phase is this? Which phase is this? Pressure is a phase? So as we increase pressure and decrease temperature, as I decrease temperature, where we become solid, and as I if I really compress something, I will eventually turn it into a solid, right? So this is solid. As the pressure is going up, and as the temperature is going down. So as we lower temperature, we tend to go to make it more solid. Also, if you really squeeze and compress something, you will eventually turn it into a solid. So over here, the temperature is increasing, and the pressure is getting less. So what's this? This is gas. So pressure is going down. So pressure is going down, temperature is increasing. And what would be in the middle between these two? Liquid. Another way is draw a line that goes through all three regions. So this region, and this region. We know that if we increase temperature, it's going to start out as a solid. As we increase the temperature, it's going to start melting at this point and become a liquid. At this point, it's going to start boiling and become a gas. This point right here is called what? Triple point. And this point right here is critical point. Would someone run to the printer? We'll work on this together. Teacher's lounge. Teacher's lounge. No. Yeah. Bring it back. Geez, how long does it take to go to the printer and back? Did it not print? My printing is screwing up. It's alright. I'll just put it on the screen. So, which section represents the solid phase? So, A, which section represents the liquid phase? So again, we can draw a line. So here's one line already done. So at the lower temperatures, it has to be solid. Then we're going to start melting right here. Now we're in the liquid, and it's going to increase and become a gas. So which letter represents the gas phase? B. And which letter represents the critical point? The critical point. Yeah, it's E. I don't know why they use lowercase. Oh yeah, because they wanted to do the regions and then the point. What is the substance's normal melting point? What does it mean by normal? What do you think it means? Standard. The normal pressure. The normal pressure is at 1 atmosphere. So what is this melting point at 1 atmosphere? 60 degrees. Melting is when it goes from a solid to a liquid. So this right here is when it starts melting at normal temperature or standard temperature. Or standard pressure, I mean. So what is the substance's normal boiling point? 100. Above what temperature is it impossible to liquefy the substance, no matter the pressure? At what temperature is it impossible to liquefy the substance, no matter the pressure? So, what I say about this region up here? The supercritical fluid is where it's no longer a gas or a fluid. So at 110 degrees Celsius, it can no longer exist as a liquid. So the critical point is a point in which liquid no longer is counted. We can still be a gas. So again, so looking at this image right here, at this temperature here, so for CO2 is 300. At this right here, no matter the pressure, it can either exist as a gas, a supercritical fluid, or a solid up here. But what it can't exist as a liquid. So no matter the pressure after that temperature, no matter the pressure, it's no longer a liquid. We can drop below a certain pressure and make it a gas. We can also increase it to some pressure to make it back a solid. But at this point, during this section here, it's not considered a gas or a liquid. It's only considered a supercritical fluid. But there is a region in which you can't be a liquid after a certain temperature. So above 110 degrees Celsius, it can no longer exist as a liquid. It can be some sort of fluid, but we can't call it a true liquid. At what temperature and pressure do all three phases coexist? 45 degrees and 0.5 atmospheres. Would an increase in pressure cause this substance to freeze or melt? Would an increase in pressure cause this substance to freeze or melt? So let's look at it. So if we're right here and I were to increase pressure, it'd start freezing. If I'm right here, it would be deposition. But notice that there's no point in this whole diagram would pressure ever make something melt. I did want to show that's actually a very good point. Very good question. Look at water. There's a way that I can increase the pressure and make it go from a solid to a liquid. You can actually melt ice with pressure. By increasing the pressure, you can turn solid ice into liquid water. And yes, as soon as the pressure, so let me look that up. Cutting ice with wire.
Most people know that you can melt ice just by putting salt on it. Salt decreases the melting point of the ice, meaning it'll melt faster. What's another way to decrease the melting point of ice? The answer is you apply pressure to it. Tonight I want to do an experiment on regelation. Regelation means you apply pressure to ice and so it turns into water, but when that pressure is removed, it turns back into ice. I have two pairs of 1.5 kilogram weights. This pair is joined by a bit of fishing line, and my other pair is joined by some copper wire. They're both the same thickness. Now I'm going to put the wire and the fishing line over this block of ice and try to pull it through the ice. And I want you to make a prediction. Which one will pass through the ice first? Will it be the copper wire or the fishing line, or will they both pass through at the same rate? Make your prediction now. You got about 5 seconds left. Quick, pick one.
What do y'all think?
All right, we're ready to do this experiment. I have the two 1.5 kilogram masses separated by a copper wire, and my housemate and assistant Colette has the two 1.5 kilogram weights separated by some fishing line. They're both the same thickness, so we're going to put them on simultaneously and see how they go in cutting through the ice. How's yours?
So same weight, same pressure. The only difference is the substance. So again, the ice isn't really melting. It's actually traveling through the block of ice. It's melting at the very edge of the wire, but it's immediately freezing right back.
All right, we're roughly halfway through the experiment, but I ran into trouble. The copper wire actually pulled out of these weights, and so they fell to the ground. At this point, it looks like the copper was doing slightly better than the fishing wire, but I've had to rig up a new copper, and so I'm going to try it in a different spot and let this new copper compete. I also scraped off the insulation. There was some enamel coating on the copper wire, so I've scraped that off, so it should just be straight copper wire now. So let's see how it performs.
You should have just edited the video. And remove the mess up.
Alright, it's 1:30, but it looks like the experiment is over and we have a winner. The copper wire pulled clean through the block of ice, while the fishing line is still stuck in there. So why was that? Why is the copper better able to pass through this ice block than the fishing line? Well, I think the answer may have something to do with thermal conductivity. The copper is a better conductor of heat than the fishing line. That's important because as the wire passes through, the ice refreezes once the wire has passed, and that releases heat. If that heat is transferred quickly, it passes to the ice below, melting it and allowing the wire to move further.
So remember, as it's refreezing, so the pressure is causing the water to turn, or causing the ice to turn into water. As it moves back, it's freezing up here. And when you freeze, that means it's releasing heat. So for the case of the copper wire, copper is able to better conduct heat away and absorb it. So this heat that's generated during the freezing up here goes into the copper wire, which then goes into the front ice, allowing the copper to move faster. But notice that's still an entire block. At no point did he actually cut this in half or remove it. It's literally they're generating a high amount of pressure right here. And even though it doesn't look like it, this is getting slightly less. So that water is right at 0 degree. Ice is right at 0, and just a little bit of pressure is causing it to melt.
And faster.
Let's see if I can find proper definitions of this. So when dealing with these systems, we have two things we need to be are dealing with these problems. We often have to think about what is our system and what is our surrounding. When I say that heat is being released, that means that heat is going from our system into the surrounding area. The system consists of the molecules which are reacting or what is undergoing the phase change. So we consider the system the target of what we're looking at. The surrounding is everything else, the rest of the universe. So, for example, let's see if this actually provides. So the system includes the molecules that are reacting, are the molecules in the target of our focus. If we're looking at ice, and ice melt, as we're watching ice melting, ice is our system, and everything else is our surroundings. So an ice cube is placed into a glass of soda that is on the countertop at room temperature. For the phase change of an ice cube, what would be considered the system? So if we're so again, the system is going to be the target of our focus. The system is going to be the individual ice cubes. What would be considered the surroundings? The air, the glass, the soda. The soda itself would be considered the surroundings. So how would you describe the flow of energy between the system and the surroundings? So our system is, I wish I could have printed this out for you guys so I could be writing and showing y'all. But so the system is the ice cube. The surrounding would be the soda, the glass, and the air. Why do you put ice in the Coke? To make the Coke colder, make the soda colder. So you could describe as heat leaving the Coke and going into the ice, right? So the flow of energy is leaving the Coke and going into the ice. So heat is leaving the surroundings and going into the system. So would this be endothermic or exothermic? but we only focus on the system. It'd be endothermic. So energy going into a system is endothermic. Again, it's relative. You're right. It depends on what you consider the system and what you consider the surroundings. Usually the target of focus is the ice cube, where the ice cubes are melting and undergoing the phase change. They're doing something, right? The Coke is only changing temperature. The ice is physically doing something. It's undergoing a change. So liquefied iron is held in a still tank. The iron is allowed to freeze to solid at 125 degrees Celsius. For the phase change, and this should be of the steel, not ice cube. For the phase change of the steel, what is considered the system? Or the iron? So if you have a liquefied iron in a steel tank, what's considered the system? What's considered the surroundings? So this is the thing undergoing a change. So liquefied iron would be your system. The steel tank would be the surrounding. And how is energy flowing between the system and surroundings? So the liquefied iron is cooling off. Yes. So, and then from there it could be going out in the world. But again, we consider the surroundings everything else, so the steel tank and everything else too. So the energy is leaving the liquefied iron and going into the steel tank. So is this endothermic or exothermic? Be exo because it's leaving the system. Describe what happens in terms of energy flow between system and surroundings when solid CO2, dry ice, sublimens into gas or fog. So when CO2 sublimes, what happens? So our CO2 would be our system because it's doing something. It's undergoing a phase change. So is energy going into the CO2 or leaving the CO2 when it sublimes? What's causing it to heat up? I mean, like what? So in order for it to go from solid to gas, it has to be heating up, right? So energy has to be going into it, right? Do y'all recall all the endothermic phase changes? Where are they? So endothermic means energy is going in. Yes. So sublimation, melting, vaporization, or evaporation. Exothermic is when the energy is leaving. So that'd be during freezing. You have to imagine energy has to go somewhere, and it's getting colder. Condensation and deposition. So are y'all comfortable with phase change and heating curves? So I think I'll do a test review Monday, and we'll have a test Tuesday. It is literally going to be just like this. It's not multiple choice. It's literally like this. It'll be a heating curve. It'll be a phase diagram. And the last problem will be a surrounding versus system. So again, system is the something that's reacting or changing. Yes, the main target. The surrounding is everything else mentioned in the problem. So here it's everything else is just a glass of soda. Here it's just a steel tank. You can also list off everything else, the air, too, if you wanted to. But if you just include steel tank, if you just include soda and glass, or just glass of soda, that's acceptable too. But we'll review on Monday. If y'all have any questions and don't understand something, be prepared Monday to ask. Here's a code word for remote learners. Do you have any questions now? Hopefully I'll have the printer working. I'm actually going to go right now and well, again, so when it's turning into if you have some super cold water and it's -5 degrees Celsius, it really wants to be a solid. So when this turns into a solid, what could happen is so when this turns into a solid, it's going to release some energy. It's a phase change. So that energy is going to end up going, and we're going to end up with a block of 0 degrees Celsius ice. And if we didn't have if it released too much energy, we'd end up with 0 degree water too. So it could either be like this, or if we have a smaller container, what could happen is we could end up with something like this, a block that is -2 degrees Celsius ice. So so it could either turn into like -2 degrees Celsius ice, but if there isn't enough energy or if the energy released, if it's too much, basically you didn't cool this down cold enough to freeze the whole thing.